Hey there, how's it going? So in the previous video, it was established that the derivative of sine x is cos x, but we just did some theory there and didn't do any examples. So just to start off, we'll try using this new rule. So let's say differentiate something like this function over here. So 5 times sine of 3x. So we've got a constant multiple of a function and this kind of fairly simple function inside our function. So if we've got a constant multiple times a function, the derivative will be that constant multiple times the derivative of this. And so since we've got sine with something to do with an x inside there, using our new rule, sine x goes to cos x, sine will go to cos of the same input function there, and then also using the chain rule, we've got to times by the derivative of the brackets, the derivative of this 3x in here, which is 3, and then we can just tidy up 5 times 3 is 15 cos 3x. Alright, let's try another one. Alright, so here we have sine, again, of some function to do with x. Nothing plus, minus, times outside, so we can just go ahead and use our new rule. Sine differentiates to cos. Cos of the same thing. And here we've got to, again, multiply by the derivative of the brackets, which is negative 1. So to tidy this up, let's just write it out the front. We've got negative. And if you remember pi on 2, like 90 degrees minus x, this is a complementary angle result. Because if you think, like, for example, sine 30 degrees is a half, and so is cos 60 degrees, and they're complementary angles. So 60 comes from 90 minus 30, or in radians, pi on 2 minus this way. So we've got our negative there, and cos pi on 2 minus x, the complement of x will actually be the same as sine x. Oh, hold on a minute. What did we have over here? Same thing. Complementary result, sine of pi on 2 minus x. Isn't that just cos x? Haha, I've tricked you into learning another trig rule. Cos x, if we started with this, is equivalent to this, which differentiates to this, which is equivalent to this. So we actually have a new rule, which is that if we have cos x, and this is going to differentiate to negative sine x. So cos and sine, if you differentiate them, will kind of ping pong back and forth between each other, and like sine goes to positive, positive goes to negative, and then if you differentiate, say negative sine x, well, sine goes to cos with a negative slapped out the front, and it kind of cyclically goes if you keep differentiating positive sine, positive cos, negative sine, negative cos, back to positive sine, and they kind of keep spiraling around like that. Okay, so let's try an example using this rule now, new rule now. Just let me touch harder. Alright, so here we have a product of two functions, x squared and cos of something with an x in it. So here we should use the product rule. So I'm going to say x squared is my u, cos 2x is my v. And then we'll do these little mini differentiation problems here. So the derivative of x squared is bring the power down, subtract 1 from the power. And using this new rule, cos differentiates to negative sign, which means cos is going to go to negative sign of the same thing, 2x in there, function of x, and times by the derivative of the brackets will be a times by 2 as well. So now we can use the product rule. We've got u dash v plus v dash u, which is the order I prefer to do it in to match the quotient rule. So then we can find the derivative here by doing 2x times cos 2x plus x squared times, and then we've got negative 2 sine 2x. Alright, and it might be worth noting that we've got a common factor of 2x. We can take out both of these functions, terms rather. So we've got 2x outside of cos 2x minus another x sine 2x. Alright, product rule. Let's try an example with the quotient rule. Alright, so this will use both of our new rules together. Alright, so in the numerator we've got u is sine x, and the denominator v equals cos x. So our little mini differentiation problems, we'll do the derivative of sine x is cos x, and the derivative of cos x is negative sine x. Alright, so now we can use the quotient rule. We've got u dash v first minus v dash u all over v squared. So we're going to have cos x times cos x minus negative sine x times sine x all over v squared, so all over cos x squared. It's squeaky. Alright, so we have cos x times cos x in the numerator, which is cos squared x minus a negative is the same as plus, and we've got sine squared x all over cos squared x, and then hopefully we notice in the numerator that we've got the Pythagorean identity, that cos squared plus sine squared is 1, and 1 over cos squared is the same as 1 over cos, the whole thing squared, so this is actually sec squared x. Oh, hold up a minute, we've done it again. Isn't sine x on cos x something else we already know? That's tan x. I've tricked you again. Tan x is the same as this expression, which we've shown differentiates to this expression. So we actually have a third rule that the derivative of tan x is sec squared x. Alright, so now we've got 3 different differentiation rules for our kind of 3 main trig functions. Let's do an example trying using this one. Let's say let's differentiate this. So first of all, we've got a constant times our function, so we'll just keep that out the front. And then using our new rule, tan of x is going to differentiate to sec squared x. But we don't just have x, we've got x on 3. And x on 3 is the same as if we had to write d over 3 as a coefficient, as a third x, and using the chain rule multiplied by the derivative of the brackets is derivative of x on 3 is going to be a third, and then we can just tidy up 6 times a third is 2. Alright, don't worry, I'm not going to trick you into learning another 3 rules. Let's maybe investigate the reciprocal trig functions. We'll start with sec x, but I won't. We'll actually start with writing down and then see what happens. All right. Let's say we've got sec x. So just like I've kind of gone from here, we could have started here and gone to here and gone from here to here. Right. Notice, for example, like the tan x one, I got it in terms of sine and cos because we know their derivatives. So sec x should hopefully be known that is the reciprocal of cos x, and then cos x underneath 1 we can write as, using our index laws, cos x to the negative 1. Now it's in a good format that we can differentiate because we've got a function with a power, so we can use the power rule there, and then when we use the chain rule, we also know how to do the derivative of cos x. So now that it's at this stage, we can now take the derivative. So we're going to bring the power down, subtract 1 from the power, and then times by the derivative of the brackets. So the derivative of cos x is negative sine x. Alright, now here we've got negative times negative is going to become positive. We've got a sine x, and cos x all squared is going to become, cos x to the negative 2 is going to become cos x to the positive 2 in the denominator. I'm just going to break this up into, we've got a, we've got, just to pair off our 1 sine x with one of our cos x factors on the bottom, and you'll see that means we're left with 1 on cos x, which was originally sec x times, and sine x on cos x, like over here, is tan x. Alright, so that means we've got another rule, which is that sec x will differentiate to sec x tan x. Alright, I'm not going to go through the derivation of our other 2 ones. I will just state them, but it might be a good exercise to try and do them yourself. So, for example, we've got, let's just do cosec x first. Cosec x, that function we're starting with, and what's it going to differentiate to? So you could do the exact same kind of reasoning. Cosec x is the reciprocal of sine, represent it like this, use the chain rule, and then convert it back into some other functions, and you're going to end up with negative cosec x cot x. And then again, our last trig function is cot x. And what does it differentiate to? Well, you could use some very similar reasoning here. Just like our tan x is sine and cos, well, cot's kind of like the reciprocal of tan. So you can represent cot as cos on sine, and then if you do all the steps properly, you should get that this is negative cos x squared x. All right, one more example, just for a little bit of fun. All right, so let's try at least using our new sec x rule. And this will obviously assume that you've, whether through me or otherwise, know how to do log differentiation, okay? But log with a trig function inside. So the derivative of natural log of something is this function is going to go in the denominator. And then in the numerator, we're going to have the derivative of that function. So we've got the derivative of sec x is sec x tan x. Plus the derivative of tan x is sec squared x. All right, now in the numerator, we've got a common factor of sec x we can take out. So we've got sec x outside of tan x plus another sec x all over sec x plus tan x. And then we've got a common factor in the numerator and denominator we can divide throughout by. So we get that the derivative of natural log of sec x plus tan x is sec x. So I guess that's kind of interesting because sine goes to cos, cos goes to sine, okay, and the sine, S-I-G-N, changes, but all these other ones, tan goes to sec squared, sec goes to sec, but times tan, I mean, like, what function just goes to plain old sec? So something might be a bit of fun to do would be see if you can come up with a function which will differentiate to just tan x, or just cosec x, or just cot x. And you're going to have to play around a little bit with starting with differentiating log function. So have fun. That's it for this video. Catch you later.